So I was just talking to Nancy, trying to remember how many years it's been I've come and talked to first-year med students, and the center has been up and running since 2008, so it's got a 10-year anniversary, which is really something, because this was a vision that Dr. Sutton had for many years, and it came to fruition, and I can't believe 10 years has gone by. Geez, I feel old. But I've been lecturing here for about 9 years, and so this is the first year I'm using a new slide deck, so you guys are lucky. So everything's like last minute, so you recycle the slides. You're like, oh, I'm not going to change it, but this is a whole new slide deck, so you guys are totally lucky. But first thing I wanted to say is that I congratulate all of you, and I'll tell you why, because you're different. In my experience in interacting with the med students here at Baylor for the last 9 years, the ones that are interested in space medicine are the out-of-the-box thinkers, the ones that are willing to take a chance on something that's outside their comfort zone. And frankly, I think we need more of that in medicine. I think that we're taught a lot about, checklists, and this is the protocol, and this is what's medically accepted. And sometimes you have to stray outside of those boundaries when you have a patient that's presenting something a little bit different. You have to be a little bit more creative. I know creativity in medicine shouldn't go hand in hand. It's kind of scary when you tell that to educators in particular. But I think the case I'm going to make to you today is that because we're thinking about medicine in space, healthcare in space, we do have to be creative. And so it gives an opportunity to all of you to think of healthcare and medicine in a new way. So I'm hoping that you walk away being a little bit more creative, but you're already halfway there, you're here, so I congratulate you on that. So I'm going to talk to you today about how space is actually, to me, the final healthcare frontier, and this gives me away, Star Trek, not Star Wars. That's my thing, and so if you go to look at LinkedIn, my profile picture is in a Star Trek costume, so go and check it out. I look good. Anyway, so we're really fortunate that here in Baylor we have something unique nobody else anywhere around the world has, and I can't tell you how lucky you guys are. And Dr. Sutton gets hundreds of emails from medical students all over the world wanting to do space medicine. And it's pretty hard for us to engage them. You guys have something that so many other students have. So again, you're very lucky, and proud of you guys for being here. All right, so what is NASA thinking about? NASA's thinking about exploring space, and when I say exploring space, we're already in space right now. But we're in what we call low Earth orbit. It's still pretty safe. We're in the protection of our magnetosphere. If we have an emergency, 9 hours, we're back. We're in a hospital, no problem. So we're really fairly protected right now with the International Space Station. And we've been doing it for decades. We know how to do this. But although many, many years ago, we did go to the moon and back, we did step on the moon, we've never explored real deep space, and that is beyond the moon. And the destination, of course, is Mars. So what is NASA thinking about? So essentially, it is thinking about in the 2020s, so here we are, 2018 is almost over. In the 2020s, they're planning to put in cislunar orbit around the moon, essentially, a deep space gateway, and build in the vicinity of the moon a deep space transport. So from the moon, this will go to Mars in the 2030s. Now, this is really ambitious and aggressive. Now, it's a plan. We always know that things may shift to the right. But because NASA's working with this aggressive plan, we are being charged to help them solve some of the health challenges that we're going to have in being far away from Earth, essentially. And when you're in cislunar space, you're no longer protected by the magnetosphere of the Earth, so you'll be exposed to space radiation. And of course, on the long trip to Mars, which can take 7 months or so en route, and then you have to be in orbit around Mars and then come back, total round trip is roughly 30 months with current capabilities. That's a long trip to be exposed to space radiation. But we'll talk about some of those health hazards in being in space for that duration. So that's what we're working towards. So what are the challenges of being in space? There are a lot of challenges of being in space, but here are the big ones. Reduced gravity, and I'm sure you've talked about this since this is one of the last lectures. I'm sure you've discussed the reduced gravity and how it affects the bone, muscles, heart, etc. There's also the radiation environment, and we just talked briefly about that. And then lastly, and maybe you haven't talked so much about that, is isolation. Now, Right now, the astronauts are isolated from their family and friends, but they can call down anytime they want. They interact with Earth all the time. When you're in deep space, you may have communication delays up to 40 minutes cumulative, 20 minutes each ways. You may even have communication loss for up to 2 weeks, depending on where you are. And you will be in a much smaller space. You will not be able to contact your family as easily, and you're not going to have the internet. You can't go check Instagram. So this is quite a different scenario than what we're working with today. And imagine being cooped out in a tin can for 30 months with 3 people that your boss or your professor picked for you. So it's not like you get to go with your best friends, okay? So, and sometimes the decisions are made of who goes together based on the skill set. Hopefully they'll consider the team composition as well, how people interact with each other. But the isolation is something we are worried about. So we'll talk just a bit about that. So I present to you the possibility that space really is the final healthcare frontier, because we have to think of providing healthcare. And when I say healthcare, and the reason we called it space health and not space medicine, is it's about prevention. You never want to get to a point where you actually have a medical condition that you have to treat. We have to be very vigilant. We have to be proactive. We have to prevent a health situation from becoming a medical situation. So we're going to be relying on the actual astronauts to be the providers themselves, to be monitoring themselves and their own health. And even though I believe NASA is considering that at least one crew member will be a medically trained person, it's very likely that that physician may in fact get ill. So you may have a geologist having to do a medical procedure on that physician. So in thinking about this, and this may be really scary, you're here to learn how to be physicians. You certainly don't want average Joe doing a medical procedure. But there's going to be some things that we're going to have to entrust to the patient themselves. And in thinking about that, it's enabling your patients at home to do their own monitoring. So it's a similar kind of scenario. So we'll talk a little bit about how putting the healthcare vigilance, essentially, or the monitoring in the patient's hands actually makes it a better situation, healthcare here on Earth. All of the things that we're going to provide, when I say by things, I mean technical capabilities in terms of ultrasound scans, or near-infrared, or pulse oximeters, or blood chemistry analysis, all of those things. We're not going to have the ability to send samples up to the latest, to the nearest lab to do chem analysis. Everything that we send up in space has to be miniaturized, has to be incredibly robust. We're not going to be able to trade out or upgrade software very easily. We're not going to be able to provide consumables if they go bad. And so a lot of the healthcare really has to be very different than how we provide it here on Earth that we take for granted. And I will show you a slide that I hope will convince you that we have very similar concerns in space that we do on Earth. So the value proposition is that because we're setting the bar so high for health and medical care in space, we're actually creating new ways of doing things here on Earth because we have to. And so one of the examples, and perhaps you talked about it, is how to treat kidney stones. Because we were worried about kidney stones for astronauts, we had to come up with a new way to treat kidney stones, which has now made it to a new standard of care. It's being tested in emergency clinics here today on Earth, how to move kidney stones to clear them in a new way that will someday become the new standard of care going forward, because we had that problem with astronauts in space not being able to go for surgery to remove kidney stones. So what if going to Mars is actually going to give us the healthcare system that we need here today? And what do I mean by that? What I mean by that is that enabling the patient at home to be extra vigilant, to be able to monitor certain things, to work in concert with the provider so that we can prevent medical situations from occurring. And with, just like the kidney stone example, to be able to reduce the cost of providing that kidney stone treatment, because you no longer need surgery. You have something non-invasive like an ultrasound that you can do immediately in the primary care physician office or in the emergency room, rather than having to go to a urologist and having to do a surgical procedure. So by solving for space, we're actually making healthcare more affordable here on Earth today, because we're making it a little bit simpler. So this is the slide that I want to show you. This is the only one. This is replacing a slide that lots of other people have showed before, all these different things that go wrong in space with human physiology. But I actually developed this slide for a talk I gave at the Huffington Center for Aging here at Baylor. So the Huffington Center for Aging is working in a lot of these different areas, and in all of these conditions, actually, you see a lot of these changes in astronauts is just accelerated. So for example, sarcopenia, loss of muscle. So if you don't properly exercise, the reduction in gravity can cause loss of muscle. Osteopenia, you can have vision alterations. You can have cataracts develop because of radiation effects. Kidney stones are seen in elderly people. Nutritional deficits, balance disorders, et cetera, et cetera. You see increased viral shedding because of reduction in immune function. All of these things that we see in an aging population, a higher preponderance of development, we also see in our astronauts, and we're worried about them. And even radiation, I will argue that radiation does increase the risk for cancer, and we also have those concerns for aging population as well. So the Human Research Program is our partner in this endeavor to solve the problems for humans in space. And what they've done is they've identified all those different problems that we saw on the previous slide and many more, and gave them names. So for example, renal stone formation is one of the risks. Team performance decrements is one, so they're worried about behavior and how the teams will interact. Orthostatic intolerance is another risk, et cetera, et cetera. And you can see them organized here by priority in that they gave it a stoplight chart, with red being the risks that we don't believe we can solve very quickly. And up here you see a timeline. So this is the federal fiscal year. We're now in fiscal year 18, 19, 20. This is where the ISS is supposed to end. They're now talking about extending it to FY28. But the reason that it's important for us to have the ISS is to test all these medical procedures in microgravity. We really need that platform to test it in astronauts in space. But as you can see that some of the top risks here in red are radiation, cognitive or behavior conditions, so behavioral medicine, that gets back to the isolation problem that we talked about, as well as the team performance, that's a red risk. Inadequate food and nutrition. How do you make sure that they get a properly balanced diet? You've got to send a lot of foods, and some of those foods and nutrients actually degrade. So over a 30-month mission, plus the time that it takes to put the food on board the ship, we're going to have a problem with certain vitamins degrading. Renal stone formation is one. Spaceflight-associated neuroocular syndrome, we'll talk about that, so I'll skip it for now. And then medications. How do you ensure that for those 30 months, the medications that you absolutely need, like those antibiotics, don't degrade? So most medications, if you look at what's in your medicine cabinet at home, degrade within a year and a half to 2. And so a 30-month mission, you're already beyond that, and plus the time that it takes to actually put the medications into storage for the travel. And then this is a huge risk right here, in-flight medical conditions. There's like a billion of them. There's at least 200 that NASA's identified. So this is actually all lumped into one condition here. I don't know why they think they're going to solve this by FY19, but okay, they're being very optimistic here. But the top red risks are the things that they're concerned about. There's others down here as well. Bone fracture, for example. They think they solve this because they think that with exercise and vitamin D, that they're going to be able to prevent bone fractures. Okay, hopefully. So our mission in the Translational Research Institute for Space Health, and our acronym, we just love the fact that we're in Houston, Texas, and the acronym is TRISH, which sounds like a soccer mom with big hair driving a minivan. I'm okay with that. I'm okay with that. So anyways, what we're supposed to do is translate cutting-edge emerging terrestrial research to applications for space. So what does this mean? It means that we have to help NASA reduce the risks to health and performance. And how are we doing that? So what we're doing is investing in 3 things, and it took us a while to figure this out because NASA basically said, oh, just translate the best things out there and bring it to us. We don't know what we want or what we need, but we'll tell you when we see it. That's essentially what it was. So we had to figure out exactly what it was that they were already doing that they needed us to complement. And essentially, what they were looking for is they didn't have a good connection to the best medical schools in the country, for example, Baylor, or other places like Harvard and MIT, and they don't have a med school, but Caltech, for example, are technology places where people are solving for very difficult problems. And so they want to know what's out there that is changing the face of medicine and healthcare and technology, and how can we use those inventions to help us in the space environment. So basically, it's what NASA or the Department of Defense calls high TRL-CRL. TRL stands for Technology Readiness Level. CRL stands for Countermeasure Readiness Level. So it's essentially high TRL-CRL are things that are already medically being used, clinically or FDA approved, or in use operationally in space. Low TRL-CRL are just a glimmer in your eye. I have a great idea. Okay, so that's a low CRL, TRL project. So we're also interested in those, the glimmers in the eyes. So the audacious emerging solutions. So somebody has a crazy idea about how to do something, and nobody thinks they can get it done. Well, NASA's actually given us a mandate. Go ahead and invest in those things. Let's see if they can really make a difference. And for the most part, they're not going to work out. But it's okay because that's how you drive the innovation engine. And then finally, investing in a talented creative workforce. You all are part of that. So part of my time is actually being spent here to talk to you all about how do we change healthcare so that we can use it in space. So how do we do this? Most of our work really involves giving grants away. So we take the tax dollars that NASA is given by the federal government. So they have a budget, and a piece of that budget comes to Baylor. And what we do in the translational research program, we take that money and we give it to other people on a competitive basis. So we decide, gee, we need to study how to do a better surgical procedure in case we do have a kidney stone and use ultrasound. So that was, for example, what was done in the previous institute. So we gave a grant on a competitive basis to a group at University of Washington, for example, that did the work to develop it. So it's grants. And it doesn't have to be university, they can be companies as well. In fact, a lot of the work that we do is partnering with small companies who have those technologies that are ready for market. So those are the high TRL, ready for clinic, ready to show proof of principle in humans. The supporting program essentially is we have a lot of educational materials to explain to people, hey, guess what? The problems we're solving in space are the exact same problems you're solving on Earth. You're not just going to develop that device for 4 people going to Mars. Your market's going to be a lot bigger. And the reason that's important is we have to partner with industry to get the products out to clinical trials, to FDA approval, to marketing in the hands of you all, physicians and patients, to actually make a difference. And then the scientist program. So we have postdoctoral fellowships. So if any of you are doing an MD, PhD, or have friends who are graduate students or thinking about a postdoc, we got money. We can fund salary support for postdoctoral researchers. And they have to be, I think, within 2 years of getting their PhD. So get the word out. We're about to put out another solicitation next month, mid-May. All right, so who are we exactly? I know it took a while to get here, but I had to kind of hook you in to show you why it's important that you care. We're funded by the Human Research Program at NASA through a cooperative agreement. And actually, that cooperative agreement comes up to the Center for Space Medicine that runs this course. So we're all part of one big happy family. This grant actually came to Center for Space Medicine, to Baylor, in a consortium. And Baylor partnered up, since we are leading medical school, we needed to partner up with technology universities. And so Jeff Sutton was very strategic in selecting Caltech, which is an absolute jewel of a place. I just visited them last week. Very small university, 265 faculty only across all disciplines, but just the most creative and unusual people, really out-of-the-box thinkers. So that's on the West Coast, and then MIT, of course, stands out as an amazing technological workhorse for the country, and a lot of inventions coming MIT on the East Coast. So we're partnered with them. So how do you find out more about the top risks and how they relate to some of the problems that we have here on Earth? We actually have what we call the Red Risk School, and we just had it a couple weeks ago, and we're going to continue having it next year as well. And we've just archived a seminar, a bunch of seminars online. And so you can go to our website and find it. And this is from the top experts at NASA and in the leading disciplines, essentially. And they describe the latest findings. So if you're interested in the neuroocular syndrome that we're going to talk about, there's a talk there, very recent findings of the latest astronaut results from the experts. So you can go there and find out more. There's also a talk about space radiation. There's a talk about nutrition and analogs. What is space like on Earth? Okay, we also have virtual workshops and seminars. So for example, we have a seminar series. We have April 25th next week, Mikhail Shapira from Caltech. And okay, I know this is ultrasound, boring old ultrasound, but this guy has a way of using ultrasound to control and visualize cellular function. So what do I mean by this? It was a Nature paper about a month or two ago, and essentially he's made bacteria report out activation, okay? And you activate them based on whatever input you want to use, essentially. So if you want the bacteria to be responsive to radiation, for example, as a biodosimeter, a readout of whether or not you received radiation in this part of the body, what you do is you would put something upstream of the bacteria, or what I mean by upstream, something that would regulate the bacteria that's responsive to radiation, and they produce gas bubbles that are in these particles, and you can use ultrasound to quantitate the gas, how much gas they produced. Okay, so that's just one crazy example of how this thing can work, but I can't even think of all the millions of applications that this new technology, is a brand new technology that he's developed. Cellular function with ultrasound. So not whole body, but actual minute and very small physiological changes. So he's going to talk about this new technology next week. So tune into that. It's all online virtual workshop. You can find it on our website. And we also have Artificial Intelligence in Space Health Pocket Doctor. That's what we're calling it, or the E. McCoy. If any of you have ever seen the old Star Trek series, Dr. McCoy was the doctor. We're thinking about providing decision support for some of these geologists and scientists who are going to be on the way to Mars, and the physician gets sick, and this physician has acute abdominal pain, has passed out, or whatever. So this would be a way to help them augment their decision support if they're not in communication with Earth. So we're going to be talking about artificial intelligence, the use of that in healthcare. So again, check our, it's open to the public. You guys can join virtually on July 31st. There's links from our website. All right, so we're going to talk about a couple of conditions. And have they seen VIP? Have they seen SANS? Yeah. Okay, so everybody talks about this syndrome because it's such an interesting medical syndrome. And I apologize to you if this is a repeat. I'm going to go fairly quickly through it. So it's it's been renamed so many times. It used to be called VIP, Visual Impairment Intracranial Pressure. Now it's Spaceflight Associated Neuroocular Syndrome, or SANS. And what's exciting about this is that it's a new syndrome. And Jeff Sutton is always saying to me, you hardly ever see a brand new medical syndrome. And so it's really interesting. It's really interesting because it helps you understand physiology. Yes, it started in space. We're seeing it in space, but what can it help us understand about physiology and anatomy and how things work here on Earth and some of the conditions that are analogous here on Earth. So I'll tell you about some of the analogous conditions. But most of all, because we're always looking for new ways of doing healthcare, in particular surveillance, we're interested in cerebral and ophthalmological technologies. And remember, the bar is set really high: miniaturized, non-invasive, non-expert user. All of these things, really kind of sets the bar quite high on these technologies. You can't do a lumbar puncture in space. to determine intracranial pressure. So what other non-invasive ways can we determine the pressure on the brain? And so if we find something that actually works, you don't have to do that lumbar puncture on that patient that you have, that child that's really wiggly. You can do a non-invasive device. So you can see how by solving for space, we're actually coming up with new ways to do healthcare here on Earth that would make it safer. So, all right, and I apologize for this very simplistic slide, but it is believed that the syndrome, one of the reasons that we may have this syndrome is the fluid shifts that occur up towards the head. So we have a fluid shift, it's a distribution, essentially it's more equal in zero gravity, if you will, rather than in 1G. And when we do know that there's a change in plasma volume, that there's a decrease in plasma volume in space, that's an adaptation to the changes in the fluid distribution. We also have another problem in space, which I don't have a slide for, which is they're in an enclosed environment. So they're breathing out a lot of carbon dioxide, which has to be essentially scrubbed from the air, and that takes power and it takes chemistry. So there's absorbance and certain procedures that have to be taken to clear the air, essentially. And it's an engineering problem, but they don't seem to be running the air at atmospheric levels of CO2. It's running at least tenfold higher than normal. So imagine, feeling the CO2 tenfold higher than normal. Imagine being in a closed space. There's 20 of your friends all breathing heavy, especially when you're exercising. You start to, have an hypercarbia, essentially, or hypercapnia. And so we know that can actually affect physiology. And so we believe that it may, in fact, affect the syndrome. So what is the syndrome? And I'm sure you've seen some forms of these slides, but the thing that we're most worried about is we're seeing papilledema. We're seeing the swelling of the optic nerve, the optic disc edema here. We believe that there is an increase in intracranial pressure that's pressing on the back of the eye, and that you can see it these are actually images in space using ultrasound, and you could see that this is the front of the eye, this is the back of the eye, and a normal globe looks like this, and you have a flattening, which could very well be caused by a pressure from the back of the eye with increased intracranial pressure. Now, in the handful of astronauts that manifested with papilledema, 7, I believe, was the number, it was medically indicated to do a lumbar puncture. You're not just going to do a lumbar puncture in all the astronauts. So when they did do that lumbar puncture, this was after flight. They had been to space, they came back, they showed papilledema. It was elevated. It wasn't greatly elevated, but it was moderately elevated. And so there is a concern that in space there may be an increase in intracranial pressure. Why there's an increase in intracranial pressure, nobody really knows. There's lots of hypotheses, and we'll talk about some of them. Fluid shifts is one, the carbon dioxide is another, drainage is another issue. One of the other possibilities is venous compliance, perhaps that there's a change in venous compliance in space because of the fluid shifts as well as the microgravity. Lymphatics, drainage is something I'm going to talk about in a little bit. The other thing that we see is a hyperoptic shift. So that is essentially because the globe of the eye changes shape, you actually get a change in vision, and it could be quite significant. 1.75 diopters is big. So imagine wearing glasses and then you wake up in the morning and everything's fuzzy and you can't go to the local optometrist office to get a new pair of glasses. So we have to send up new glasses for them. We've also funded over the past electronic glasses, smart glasses that can adjust your prescription. Okay, and then we are seeing some choroidal folds and other types of symptoms, but not across the board, across everybody. Mostly it's the optic disc edema. We're also seeing some swelling of the retinal nerve fiber layers. All right, so how did we address this condition? Well, one of the issues is that when we take a picture of the retina in space, we sent up a device, and it takes 2 people. You have to have one person stick their eyeball in it, the other person hold it straight across. We have to dilate their pupil, and then we have to scan an image. These are non-expert users. You send it down to Earth. The ophthalmologist looks at it and goes, that's a bad image. Go back and redo that eye. So it's a huge procedure every time they have to do it. And they're dilated, so they don't like doing it. They don't like dilating their pupils because they're out of commission. So we actually partnered with a company that's a spin out of Microsoft, actually, that had imaging technology and image stitching capability that was able to develop a non-mydriatic, so that means you don't need to dilate the pupil, wide angle, plus 45 at minimum, imaging of the back of the eye, essentially. Very high resolution. You just stick your head in this thing, and it does the scan itself, and it only saves images that are good. So it has a smart capability, essentially, and only save images that are good. Rescan if needed. It'll tell you, go back in and stick your head back in again. So they've gotten to a certain point where they're starting to miniaturize it. And there are a lot of folks out there, a lot of big companies are interested in this technology. So if you're an astronaut, you just want to stick your head in a viewfinder and get the scan done. You don't want to be pulling out a medical device and futzing with it. And you want essentially a smart system to tell you, hey, looks like you got papilledema going on, or hey, you took a bad image or a good image, or you may have some other condition developing. So what's the Earth application? Diabetic retinopathy is a real big one. So the biggest problem we have is a lot of diabetics don't go to the eye doctor, even though their primary care physician tells them, go to the eye doctor. So about half of them receive annual eye exams, which means that there's probably a lot of people walking around with developing diabetic retinopathy. So if you can actually do this in the primary care physician's office, you have a simple device that you just stick it on your patient. First of all, you could charge for another procedure. And second, you got your result right there. You don't need to send them out, and you can track these patients as they come in for their annual exam, getting their prescription on their insulin, their metformin, whatever it is they're taking. So I think this could really save a lot of eyeballs. Now, we talked about the condition, the SANS condition. One of the other things that we're taking a lead on that NASA is really not investigating is we actually believe that lymphatic flow might be obstructed in space. So the lymphatics, just to remind you, is a low pressure system, and we believe that with the fluid shifting up towards the head, in fact, there may be a problem with proper lymphatic drainage, particularly in the head region. And there are some studies in animals that show that cerebral spinal fluid can, in fact, drain into some of the nasal lymphatics. And so the question is in space, if we have poor lymphatic drainage, is CSF just not draining properly? And that's why we have an increase in CSF fluid pressure. So one of the things that we wanted to do is image lymphatics in space. And this right here is a video of, you have an injection site over here in the foot of a patient, and it's a trace amount of indocyanine green, very tiny amount. So it's so small it gets diluted in the blood, so you do not see it in blood. But the lymphatics pick it up so readily, and there's so much less volume in the lymphatics that the tracer can actually really, is it supposed to be, yeah, here it is. You see how it's moving here? Okay, so this is, I believe, before treatment. And then I think, so the treatment, now the treatment, you can see how it moved up. So what's the treatment? Anybody know what a treatment is for poor lymphatic flow? Something simple, so simple. Anybody? Throw out an idea. Come on. Massage. Yes, massage. So actually, this technology was shown to insurance companies so that they would pay for therapeutic massage in lymphedema patients. Seriously, it was. So it basically showed before massage, after massage. Now, yes, we can massage astronauts, but it's really about the CSF fluid, and so the right now what we're looking at is there just a change in lymphatic flow, just in the peripheral lymphatics in the head, for example, versus the legs in space. The next step will be to look at CSF. The problem is that, in order to get it into the CSF, that's a whole other level. Patients are receiving CSF injections or indocyanine green injections for mapping out tumors, for example. So that is indicated in humans, but you're not going to stick it in a healthy person. But we're going to start by looking at the peripheral lymphatics and in a head-down tilt model, for example, or if you're in a pool, okay, with your head out, the pressure of the water essentially is going to shift the fluids up towards your head. So that's another model we're looking at for fluid shifts instead of just head down tilt. So we're looking at CSF drainage in the peripheral lymphatics in the head, for example, and then lymphatics, vessel diameter, flow direction, all of these things. We're also interested in, there's certain biomarkers that one can look at in terms of what's improving lymphatic flow, what's not improving or associated with poor lymphatic flow, et cetera. I'm telling you guys, lymphatics are really interesting, and I think they're so understudied. So I'm sure you don't even have anything in your curriculum on lymphatics. But Li Hong Wang in Caltech is actually using a non-tracer used label-free photoacoustic lymphatic imaging fluorography and stimulated microgravity. I just saw this set up, and it looks really complicated, but it's really cool. They're going to eventually make it miniaturized, and essentially what it does is it uses photoacoustics, so it uses light and it uses ultrasound, and you could see that you can activate and look at the absorption, and blood versus lymph absorb in different wavelengths, and so they're actually using this to develop a system to look at all of these things label-free, which would be even better. And these folks are brilliant. They have the coolest camera system in their lab. All right, so what's the earth market? Well, lymphedema. There are patients that have lymphedema. Oftentimes it's secondary from an injury. Cancer patients often get lymphedema. You also have heart failure patients that have fluid distribution issues, vascular diseases, autoimmune diseases. A lot of the drugs that actually work on autoimmune diseases are targeted to the lymphatics. So if there's poor lymphatic flow, you may not actually have really good efficacy with those drugs. And a lot of companies are actually looking at immune drugs right now and how to target them specifically to the lymphatics rather than introducing them into the blood, where really that's not where they're doing action. It's really in the lymphatics. So now I'm going to talk about radiation. We have just a few minutes, just a few projects on radiation. So what we're doing is we're actually taking a different approach to looking at how one would understand the effects of radiation on the body, and as well as to try to come up with a way of making you more resilient. So we're actually thinking about how do we make people more resilient to the effects of radiation. And this, for example, is a project where we substituted the hematopoietic system in the mouse, so bone marrow, think bone marrow transplant essentially, with human cells, so humanized mouse. And we're actually giving radiation, and we're looking for biomarkers both in an artificial gut situation, so it's a gut on a chip, as well as looking at the hematopoietic system, testing curcumin as a radiation protection agents, but also looking for biomarkers. So the gut and the hematopoietic system, as you know, are very sensitive tissues to the effects of radiation. Cells are turning over all the time. And we're very concerned about the hematopoietic system, of course, and the immune system of astronauts in space, as well as their gut. We all know that if your gut is messed up, you're not going to be in good shape. The other two projects that I'm going to tell you about really briefly is we're actually looking for ways to make you more resilient to radiation. So what's the relevance here on Earth? So all those patients that are receiving radiation treatment as part of their cancer therapy, there's a lot of sequelae. There's a lot of healthy tissue toxicities that actually limit how much you can give a patient. So, and there are actually agents that exist. They're not FDA approved, but actually are being used clinically off-label by some radiation oncologists to protect their patients from the toxicities. So for example, you have a lot of mucositis, or you'll have skin issues, or it's known that patients receiving radiation to the breasts end up showing up with heart failure 5 to 10 years later. So there are things that you can do to protect your patients when they're undergoing radiation treatment. So there's actually an Earth market, if you will. We just haven't fully developed it. So we're looking for genes that can actually confer space radiation resistance. So anybody hear of water bears, tardigrades? They're kind of strange beasts that live in thermals and very extreme conditions. and they're exposed to radiation, they survive. And so there were a few genes that were identified that conferred their resistance to radiation. So we're going to test them in another organism. We're going to put them into fruit flies, which is a really great model system, another genetic organism that you can test really quickly with large numbers. And these transgenic flies, we're going to zap them with space-relevant radiation. And we're going to see whether they become more resistant to radiation. So we're taking a gene from a tardigrade, a water bear, and putting it into a fly. We're also going to do it in mice. Now, so what? What if we identify something that works? We're probably not going to take it all the way to making a pharmaceutical small molecule. But today, there's actually nucleotide-based therapies that you can give that are short-term, not integrated into DNA, not virus-based, that could express a gene product, protein, RNA, whatever it is that works to provide for a short period of time a resistance or a function of some sort. So that's coming. That's actually, it's ongoing now. Susan Rosenberg actually is here from Baylor College of Medicine. So she actually was looking for genes that made human cells more sensitive to radiation. She was working on cancer. She wanted to sensitize cells. Don't look at the slide. This is confusing. Just look at me. So Susan was looking for genes that make the tumor cells more sensitive to radiation. And she used E. coli. So E. coli, yeah, they're pretty far away from humans, but guess what? DNA repair has been conserved all the way from E. coli up to humans. Same types of genes, same mechanisms. It works in lower organisms. Evolution kept it all the way up to humans. So she actually identified a whole bunch of genes that actually did the opposite. When you do a screen, you get what you're looking for, but you also get opposite. So who's interested in radiation resistance? The space program. So all these genes that she basically put aside in her freezer because they were not about cancer, now we asked her to look at homologs. So she identified 78 human homologs for prevention of damage, DNA damage. So think about that. If you can actually provide some kind of a therapy to make you more resistant to DNA damage, that's an anti-cancer. It's almost a cancer vaccine, if you will, right? Because potentially what makes you resistant to radiation makes you resistant to other mutagens for DNA damage, right? So potentially this could really come up with something very interesting. And what she's doing is she's going ahead and putting them back into bacteria and eventually into mice and higher organism cells and testing them for can they confer resistance to protons, which is one of the main things we're worried about in spaceflight. So this is a very novel approach, and it was a very cool idea that Susan came up with here at Baylor. Now I'm going to talk super quick about the microbiome. So, I love this. So have any of you heard of the term microbial medicine? No? It's the future. It's the future. We're going to use microbes to provide medicine, to provide health care. So we carry half of our cells in the body are not our own, right? Half the cells in our body are microorganisms living on our skin and our gut everywhere else. So we're only half human. But we're actually worried about the microbiome, as more and more studies have shown, including here from Baylor, that even autism can be linked directly to microbiome. Yes, somebody here at Baylor. I'm seeing you guys looking at each other. Yes. So it's true. There's a brain-gut connection. We already know that the microbiome regulates your immune system. So we're actually kind of worried about this because this is what they're going to eat for 30 months. So these foods were irradiated and sterilized, et cetera, and they're not going to be getting a lot of healthy bacteria, essentially. And it turns out that when you look at, and this is a project that we funded at UCSF, when you look at space, and when you look at the stools and the skin of astronauts, now we just started this study, but there was already preliminary data, their microbiome becomes more and more limited. Guess what? They share each other's microbiome. So rather than having diversity, which is always good, right, to have a lot of diversity, a lot of good microbes in your body, they're becoming more and more alike. And there's other studies that suggest that even radiation can affect microbiome and can make and this is work that's not yet published, work that NSBRI funded, that as you apply in animals, in mice, radiation, you can have a shift from healthy bacteria to pathogenic bacteria. So we're worried about this. We're definitely worried about it. So one of the studies we're looking at is let's look exactly at what's happening in space. The other approach is actually, so your good bacteria may not be my good bacteria. Like my gut somehow doesn't like that meal you had. And so what we're trying to do here is create a personalization. Essentially, this is a gut on a chip. Okay, so it's a microfluidic device. You're going to be able to take cells from your stool, you personally, cells from your stools, your gut epithelial cells, and you're going to be able to test what is a good combination of bacteria or what is a good food to turn on the good bacteria. And here's an example of a panel of different bacteria. So there's good bacteria, bad bacteria. You want to look at diversity, you want to look at balance, and you also want to see an outcome like what's a good pH for your gut, digestive, the functional aspects of gut epithelium as well. And so the whole idea is, and this sounds so like Star Trek-y, kind of crazy, and it's very, very early stage stuff, is to be able to personalize, to take gut from your stool sample, make an artificial gut, and start to look at what's a good prescription for you rather than you taking in kombucha or whatever it is you're drinking and seeing, gee, is my gut feeling good or am I having too much flatulence or what? So rather than doing that, you would basically make it an in vitro assay. So the whole idea is to personalize the types of prebiotics that we would be giving to each astronaut. And then how do you deliver those probiotics? Well, we could send probiotic pills, but they may or may not survive the radiation. It's an additional mass that you would have to provide. Maybe they degrade, maybe they don't last long. So Bob Langer, who's at MIT, actually has this system now. It looks kind of scary. This lives in your gut. Now, it doesn't look like that when you swallow it. It's encapsulated in a very tiny pill. And he's already demonstrated that this is safe in humans. And what they're using is when it goes into the gut, it basically degrades, or not degrades, the capsule pops open. And depending on the materials that you use, both for the capsule and also for the star shape, it can last anywhere from a day to a week to a month or maybe several months. The whole idea is you provide the medicine, whether it be a drug, an antibody, or a probiotic, E. coli, or not E. coli, I'm sorry, healthy bacteria that you would have in your gut through this mechanism. Now, it's being used right now. The first application is for psych patients, for people with schizophrenia who are not medicated, who don't remember to take their pills or refuse to take their pills. You would basically medicate them through this device that would do a slow release in the gut, would live there for months at a time, essentially, and then eventually does degrade. You would have to take another pill. So the whole idea is that they're looking at this mode of administering a probiotic long-term, slowly, and maybe with a personalized prescription. So that's sort of the kinds of things we're thinking about for astronauts. So thinking about that in the future. So lastly, I'm going to come to creativity in science and medicine. And as I took this job, I was being asked to be real creative and out of the box. And people say out of the box. What does that really mean? Nobody really knows what innovation means. A lot of innovation is incremental, an improvement of what you've already done, but truly game changers, like, for example, the internet or, some of the Facebook, I hate to say it, but it's true, your smartphones, the cameras on your phones, all digital pictures. These are truly disruptive technologies. So I read this book by Ed Catmull, who's the founder of Pixar Studios. So he made the first full-length animated feature film using all digital tools. Everything used to be, when Disney used to make its old movies, everything was hand done, hand drawn, hand colored. This was completely computer generated. So they developed a new technology. But he talks about creativity, and before he actually was able to come up with, their first Buzz Lightyear, their Toy Story was a huge hit, and people actually never believed it could be done. He had called all the crazy ideas that he had in his arsenal before they were able to hit on the winner. He called them ugly babies. So the ugly babies are sort of those crazy ideas that nobody likes, that nobody believes in except for that one person that believes that this could be done. And we're actually interested in those things. We're interested in those ideas because that's where creativity is allowed to flourish. Now, most of the time, those crazy ideas really are just crazy ideas. But sometimes you get a stroke of genius, a stroke of inspiration. And we want to be there to be able to move healthcare, and particularly for space, and here on Earth forward by taking a chance on these ugly babies. So that's our new motto. We give ugly babies a chance. Haven't told Jeff yet. It's going to be our new. All right, so here are your quiz questions. Is this, okay, so how does this work? They don't do the thing anymore, so.
No, do you have an answer?
Do I have an answer? No, I'll tell them what it is. Are they supposed to write it down? What is?
They mail it in.
They mail it in. Okay, so I'll just read through the questions. You guys write them down. Write them down. Okay, so of the risks listed below, which is not considered a red risk? Oh God, this is gonna be so easy for them to look up. I thought they had to do it right here.
They got to do it right now.
Oh, you got to do it now. Okay, go. Which one? Not considered a red risk. Don't shout it out. Space radiation, space flight associated neuroocular syndrome, bone fractures, or behavioral conditions. Not a red risk. Okay, got it? Next. Okay, number 2, true or false? NASA is able to.
What's the answer? No, you can go ahead and do the answer.
Do I give the answer?
Yeah.
Oh, it's bone fractures. Okay. Number 2, true or false? NASA is able to protect its astronauts from space radiation on a mission to Mars. You know, I actually didn't talk about that. Thank you. Good. Number 3, of the symptoms listed below, which has not been associated with space flight associated neuroocular syndrome? Hyperoptic shift, change of vision, increased intraocular pressure, increased intracranial pressure, papilledema. Right. IOP is actually either normal or slightly decreased. Very interesting because everybody thinks it has something to do with IOP, but it doesn't. Of the SANS conditions thought to be induced by any of the conditions except for thank you. It's upward fluid shifts, not downward. Okay, and then last, these are so easy, I know. Administering healthcare in space will drive innovation in healthcare on Earth for all of these reasons except tricky. No. No. C, right. I mean, yeah, a lot of the things I showed you were highly technical, but sometimes they don't need to be technical. You guys are, one thing we have to be really careful is not to over-engineer, right? If there is a simple way to do things, look, everybody loves a cool gadget, and I'm actually guilty. I'm really guilty of that. I saw this, I'll show you guys a picture of it. I saw this teeny, 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 tiny, 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 tiny microchip that can read glucose and lactate. It can be set up to be inserted under the skin, last for 3 months, interstitially, interstitial fluid readout of any analyte you want. It can be set up, okay? So I'm already like got stars in my eyes. We're gonna put all these all over the astronauts' bodies to read everything. So I don't have to send up any, magical device to analyze blood. It'll just be there. But, and then you're asking, okay, interstitial fluid is not the same as blood. Okay, you can correlate the two. So once a month, you would take a little blood and you say, okay, my interstitial value is this, my blood is this, now I've got a correlation. There you go. So, so that's the future. And yes, I'm excited by technology just like anybody else, but I have to always remind myself that we shouldn't over-engineer, and I guess sometimes don't prescribe that if you don't need it, So, so that was a trick question. Anyway, thank you, and feel free to contact me. Here's my email if you have any questions. And bring me your ugly babies. If you have crazy ideas, I'd love to hear them. We might be able to fund a proof of concept project. We have money to do so. So thank you.